problem 11, this was, remember, I talked about this way of, if you had a subspace of P2 or P3, which was defined by it being 0, then we can use the factor theorem to characterize the subspace. It's like it's a very nice calculational thing to do. So, you know, if W1 has zeros 1 and 2, that means I can factor out x minus 1 to x minus 2. And in the context of being in a cubic polynomial, what's left? It's just this, right? Because if it's cubic, that's the most you can have. And so W2 had zeros 3 and 4. So that's all that you could have over there. I don't think I actually used this, all right? But this is also true. Now, what I did, though, well, I guess I did use this to say this, that it's clear from this that W1 is the span of that, and W2 is the span of that, which shows me that the dimension of W1 and W2 are respectively 2. All right? And actually, if I remembered this theorem, I'd already be done. See, because if this is 2, and this is 2, and I know that P3 is 4-dimensional, what's the dimension of the intersection? It's 0. So I've already, with just this, I could already, paired with that theorem, have that it's a direct sum. Because the intersection is 0, and the sum of W1 and W2 is everything. But here's the, and I guess that's what I did, isn't it? Oh, actually, okay, so I don't think I did that. Well, I mean, I did that, but I mean, here's a standalone proof that the intersection is 0, right? Let f be in the intersection. That means that f of 1 is f of 2 is f of 3 is f of 4 is 0. Can you have a cubic polynomial which goes through 1, 2, 3, and 4 at 0? No. And it's easy enough to prove if you use the first 3, factor theorem, a times x minus 1, x minus 2, x minus 3. But then f of 4 is a times 6. That's 0. That means a is equal to 0, which gives you that it's the 0 polynomial. The only thing in the intersection is the 0. I think many of you, outside the context of a test, could prove this. If you put your mind to it, I really think you can prove that the intersection of these two is 0 if you start recognizing that it's a question about polynomial algebra, and you know things about polynomial algebra, right? You do know things. Finally, the part 1 is just straight first isomorphism theorem. The mapping L is a linear map. Its kernel is the symmetric matrices. So the domain mod the kernel is isomorphic to the range. But it's easy enough to prove that it's onto the antisymmetric matrices, which I've done here. So I proved that the range is AN, so the range is isomorphic to the domain mod the kernel, which gives us that. So that's first isomorphism theorem, just that. Now, remember I said part of the test was hard? B is hard. But here it is. If you want a basis for the symmetric matrices, you're basically looking for something to get these parameters which are independent, right? There's then a repeating of these below the diagonal. So if you look at that, you've got n in the first, you've got n minus 1 all the way down to 1. So you're looking at n plus n minus 1 plus n minus 2. Or in other words, 1 plus 2 plus da plus n minus 1 plus n. Hey, Gauss knew this was 1/2 n times n plus 1. Doubtless you have worked this as an induction example in Math 200, right? Sum of the first however many numbers is equal to 1/2 n squared plus n, yeah? And that is in fact the dimension of the symmetric matrices. So what you need is you need a basis which has the diagonal elements on their lonesome and then sums of the off-diagonal elements, all right? So that's how it goes. There are that many of those things. And then because we know that Rn by n mod Sn is an, that proves that the dimension of the antisymmetric is n squared minus the dimension of symmetric. And if you take the difference of n squared and that, you get 1/2 n squared minus n. As a check, if you add this to that, we get back n squared, like we ought to, because the direct sum of Sn and An is all of our n by n. So many final exams I've put this on just to see if students can actually calculate the basis for symmetric matrices at that point.
Do you ever repeat questions from your test to your final exams?
Yeah, sometimes. I think I already did I already tell you guys the story about the intersection of subspaces problem? So I think, I don't know, it was 3-4 years ago. I forget exactly, but on the final exam I had you have two subspaces, U and V, or U and W. Prove or disprove that their intersection is a subspace. In that particular class, no one could do that problem. That was what convinced me that class, no one should have an A. So that's the story of how one semester no one got an A. But ever since then, but that's rare. It's rare. Usually I have 5 or 10. I don't know.
What question was that? How many F's do you have?
How many F's? Bye, Debbie. How many F's? I don't know. I've got enough already. I'd really not like to have any more. I don't really. Oh, I have them. I should give them out so I won't have so many. Oh, I see. Yes. Yeah. Bad logic. No.
What was the question that everyone failed in the final? She's ready to be done studying.
Oh, we talked about it earlier today, that the intersection of two subspaces is a subspace. What's the proof for that? I mean, it's just like 2 or 3 lines is just subspace test. And definition of intersection, right? Do you know what an intersection of two sets is? Oh. That wasn't the only reason nobody made an A. It was just symptomatic. Yeah. How many people fail? I don't know. Usually not that many.
That's what I've heard.
Yeah. People usually reform by the end, you know? It happens. Mm-hmm.
I was about to fail too.